We shall look at some passive devices now. And I will introduce an important technique and a very popular technique called the beam propagation method. Passive devices are those where you do not have external control. And they could be made just by using the waveguides and their patterns. Or even the light matter interactions are not there. So, typical examples of passive devices are Y branches, tapers, the couplers, and interferometers, etc. All using integrated optic waveguides. So, I will illustrate a couple of examples and their functionalities. They could be fabricated by standard fabrication process, which we shall discuss later on. For example, let us take the functioning of Y branch. The top view, I am drawing the top view. You have a substrate and you make a pattern in this form. So, this is a waveguide region. So, its function is to divide the power injected into at the input equally between the two output ports. There are many other uses of this Y branch. For example, Y branches are needed not only to divide the power across output ports, we can also use them to split the modes. When you are talking about the more than one mode propagating in the waveguide, we can think of splitting the modes and so on and so forth. So, these could be fabricated very easily by using the standard fabrication process. For example, we can coat the entire wafer with aluminum coating and make openings in the region where we want to diffuse and diffuse some impurities like silver into a glass. So, typical is a glass substrate and we can make them by diffusing silver ions into the. So, let us look at one more example, a tapered optical waveguide. So, the top view of the taper looks like this. So, the waveguide is patterned in the form of a taper like this. This is all the waveguide region and the light injected into the input port. The mode of the light can have a variable size at the output port. the mode width can be different at the output port. So, at the input port you have a W1 and at the output port you have a width W2. So, one of the important feature in all these examples is the refractive index profile. Is changing with propagation direction. If we say z as the propagation direction and x is the direction in which the mode is confined, we can say that the refractive index profiles along the propagation direction n is a function of x as well as z. So, one more example is an of very much use in integrated optics is a coupler. We have already talked about the coupler earlier and we have seen how the coupler could be analyzed. So, a coupler, as we have seen earlier, has got two waveguides placed close together. And of course, we need tapers to take light in and light out. So, these are the taper regions of the coupler. These are the closed waveguides. Even though the waveguides are very close together, to launch light in and take out the light, we need these tapered regions. Recall that typically these designs are very small, of the orders of wavelength of light. The widths are of the orders of wavelength of light. Typically on glass about 4 micrometers, glass or lithium bit they could be 4 micrometers. On silicon waveguides they are of the fraction of a micron, 0.5 micron typically. So, here also we have refractive index varying along the propagation direction. And one more example of an important integrated optical device is the interferometer. Called the mag center interferometer, equivalent of mag center interferometer on a waveguide. So, the structure looks like this. It has got two arms, an input section and an output section and two arms. These see the arm 1 and arm 2. These are the input sections, light launched into this and the output is taken across this port and the light is divided equally at this branch and is recombined at the output combiner, and the lengths of the arms could be different, or depending on the requirement or the function we can manipulate the light propagation in each of these branches to make very good integrated optical devices. For example, later on we will see that we can make a modulator out of this interferometer by coating an electro-optic material on top of this waveguide, or it could be made in a electro-optical material and we can use some electrodes to control the light propagation characteristics. Even here we have light propagation along z direction and the refractive index profile being variable. So, in all these examples it is not possible to solve the wave equation directly, and in general we need numerical methods to handle such problems. It is very tedious to apply the general techniques, the analytical techniques which we have seen earlier, like in the slab waveguide or the channel waveguide. So, we cannot talk about the normal modes also. We have seen that in the case of a straight waveguide, we can talk about the normal modes. At any given point, the mode can be obtained by solving the wave equation subject to the boundary conditions, and that remains same throughout. The profile is remaining same throughout the propagation direction, and we have defined the normal modes using the fields like psi of x comma z, psi of x alone multiplied by e power I beta z, where beta is the propagation constant. So, in the case of waveguides with z varying refractive index, we cannot define the normal mode as we did earlier, but we need to use what are called the local normal modes. Local normal modes are modes of the, I will take an example to illustrate. In this case, the width of the waveguide is different at each of these points, and I will describe how a local normal mode could be defined. A local normal mode could be defined as at any given point along the propagation direction, could be defined as the mode, normal mode of the equivalent straight waveguide. So, at this point at z equal to some ZL, we can define an equivalent waveguide, equivalent straight waveguide, and define the local norm and define the normal mode at that point. These can be called as local normal modes, and will be very useful to analyze the devices with z varying refractive index profile. So, at each point you can define a normal mode. Of course, the beta is different, the mode field is different, so on and so forth, and we can analyze or study these local normal modes like what we have been doing with the normal modes. So, the way that these normal modes, local normal modes could be used is as follows. We divide the given device along the propagation direction into small segments. So, let me erase once again and then get back. Okay, I will draw afresh. So, I will take an example, but the method is quite general and we can generalize easily. Suppose we have a structure like this, and at every point along the propagation direction we have the refractive index profile given, and at every point along the propagation axis we can define a local normal mode. So, the use of this technique is you can divide the given structure into several segments like this and define a normal mode in each of these segments, let us say of the length delta z, each of these segments are of the size delta z, and you define a local normal mode at each point, and then assuming that the waveguide is straight in each of these sections and knowing that the propagation is defined as e power I beta z, we can obtain the field propagation characteristics at every segment and then obtain the useful propagation characteristics. So, let me say the mode field at any section k, the input is f of k, the input beam shape, and multiply it with e power I beta k of delta z to get the field at the output of the section. So, the output of the kth section, let me say this is the kth section, at the input at this point, where is the green, and the output at this point are related as follows, and successively by repeating the process we can get the field in each of these sections, and we can say that the mode field profile changes according to the propagation direction, and we can easily observe that it depends on the profile that you take. For example, I have chosen in this example a linear taper where the refractive index or the width of the waveguide varies uniformly. We can also think of refractive index profiles which need not vary uniformly. For example, we can have a taper which is like this, non-uniform taper. So, all these can be very useful to change the mode shape in an integrated optic circuit application. So, a more accurate way of dealing with such a problem is the beam propagation method. First, let me describe the algorithm, then we will go back to the actual method. So, if you have a tapered structure or a z varying refractive index profile structure like this, we can divide this into several segments as we did earlier, but now we will divide the input profile into several components. So, we will use light propagation across each of the sections in terms of uniform plane waves. I am taking a typical simple example of the variation of this beam propagation method called the Fourier transform BPM. So, let us consider the light propagation in such a structure divided into several segments by propagating the beam in each of these regions . In each of these regions as if it is propagating in a uniform space. Okay. There are several variations of this beam propagation method. One of the popular ones, easy to understand and explain, is the Fourier transform BPM, where we divide the one of the important features of the Fourier transform BPM is that we use light propagation between segments as if they are propagating in a uniform medium of some refractive index. For example, if refractive index is N1 on the waveguide region and N2 in the substrate region, we can assume that within this region we can assume that the light is propagating in a refractive index which is average of n1 and n2. Just as an example, we can even take the n average or n uniform to be equal to n2, and noting that delta n1 and n2 are very close by, there are a lot of approximations that we can do and we can study the propagation. So, the process goes like this. So, there is an input beam to each of these sections. Let me think of a kth section. I am describing everything for a kth section, then you can repeat it for all the sections. This is k delta z, kth section of size delta z. Kth section. So, let me divide into many parts. So, the process goes like this. We divide the input beam into its various spatial frequency components. So, we know that a beam, I am just using only one dimensional, but this could be equally valid for 2 dimensions by simple extension. So, if you are given a input beam f of x, let me say f of k of x, it could be expressed as a superposition of several components f of k, or I should use some other symbol e power I, because I have been using k, let me use, I will use some other ith element, or I will use p for the I think I should change the symbols. Okay. So, what I have done here is I have expanded the given mode field or the input beam in terms of its Fourier components. These are spatial Fourier components, where P could be called as a spatial frequency. P can be called as a spatial frequency. So, we are dividing the input beam into several components. These are the Fourier components, coefficients. You can call them as a Fourier coefficients or Fourier components, and we are expanding it in the whole set of all the frequency components possible. So, I have intuitively put the integration range as a whole space where the P can take the values. So, we can also interpret the spatial frequency or the components of the input beam, each of these components, as having a different angle of propagation. Is having a different angle of propagation, because the total field propagation could be expressed in terms of the Fourier components multiplied by e power I, the corresponding propagation constant beta k into delta z. Where beta k could be expressed using the average refractive index or uniform refractive index. So, we are considering this as a uniform medium, not without any waveguide and so on. To take care of the waveguide related variations, we will apply correction factor later on. So, beta could be 2 pi by lambda into n average. So, we can relate P and beta as follows. We know that the the total wave propagation, the total wave vector could be expressed in terms of p and beta as follows. Equals no expressed in the form of k average, beta average. I will call it as so the beta for the propagation could be obtained as I will call it as beta average, that is better. I will use notation beta average or uniform. So, for every component, spectral component, spatial spectral component with P, we can obtain a propagation constant beta k. So, the propagation is in terms of, we can say as e power I beta k delta z. Obviously, only for values of p less than beta average, beta k is real, and so those are the components which propagate and sustain. Others can be thought of as getting attenuated, because this is imaginary quantity, beta k is imaginary, and all the other components die out. So, the method is, until now what we have observed is, you have an input beam, you divide into various spectral components and propagate each of the spectral component, and finally you recompose back the field at this point. So, the field, propagated field f k of x can be expressed as the inverse Fourier transform of the propagated field. Let me put it as k plus 1, f of k f of propagated field e power I delta beta into delta k. So, this is the propagated field, all the components, and then inverse Fourier transform, you get the field at this point. Now, the crux of all these beam propagation methods is, how do we account for the propagation in the waveguide? We have seen that the light propagation in the uniform medium, like in the previous example. So, in order to account for that, we need to go back to the wave equation and derive what is the extra factor that we can incorporate into this propagation, so that it represents the light propagation in the actual device structure. Let us address that problem right. Later on, I will once again re-describe the algorithm. So, let us once again start with the wave equation to derive the, we can call it as the correction factor. So, once again let me write f of k is the given profile, and f of k plus 1 is the propagated field, and we need to apply correction factor. Let me in the simplest case, I will show that we will use e power I gamma into delta z as the correction factor. By multiplying the propagated field f of k plus 1 of x into a correction factor, we can obtain the propagated field f p of x, or because we have been using p, I will use some other f propagated field. I will put it here. So, in order to obtain an expression for gamma, let us consider the scalar wave equation and expand it and substitute the expression for the propagation factor and derive what is this gamma. So, we will start with the scalar wave equation. So, del square psi plus k 0 square n square psi equal to 0 is the wave equation we are trying to solve, where this n is the important factor which is a function of z now, x comma z, let me put it x comma z. So, we will assume a field of the form psi equals psi bar x comma z e power minus I k 0 and average delta z or z. So, where k 0 is 2 pi by lambda, n average or n uniform as we described earlier could be n 1 plus n 2 by 2 or simply n 2 or whatever. So, substituting this into wave equation, we can obtain del square psi dz square plus del square psi del square psi by del x square plus k 0 square n square psi equal to 0, and differentiating this with respect to z, we can replace the z variation, retain the x variation as it is, and since it is propagating in the uniform space, we can replace with the wave equation for the uniform space, and we can obtain as follows: 2 I k 0 and average into d psi by dz plus k 0 square n square minus k 0 square and average square of psi bar or equal to 0, let me equal to 0. And of course, I have ignored the second derivative with respect to psi. So, we can ignore the second derivative factor considering that the propagation is very slow, so that we get a first order differential equation del psi bar by del z equals k 0 square n square minus k 0 square n average square divided by 2 I k 0 n average, which could be approximated to k0 square n square plus n average square, not square but multiplied by n minus n average divided by 2 I k0 n average. 1 k could be deleted with this, and looking at this factor to be very close to n average, you can replace with 2 n average and we can kill that factor. So, you could be approximately as minus I k0 n minus n average. So, the solution of this differential equation del psi by del x where this delta n is n minus n average. Remember that n is a function of z and we are taking its value in the middle of the zk in that region. So, the solution of this can be expressed as psi 0 exponential minus I k 0 delta n into delta z. So, we can say that the correction factor is k 0 delta n. Comparing with the previous formulation that we did, we can say that this correction factor is k 0 into delta n. This is a very simple derivation used to describe or illustrate how we can obtain the correction factors. We can take a more rigorous approach to obtain better values of gamma, resulting in more accurate description of the phenomena and more accurate results. So, the beam propagation algorithm as follows. So, first of all we are given n of x comma z, the structural parameter. We are also given the input field profile f of x. So, we need to divide the structure along propagation direction 0 to L into several segments. Of with delta z. More the number of points, more accurate propagation, but more computation. For every step so, we do the following operations: Fourier transform of the input field, f of k, resulting in the spectrum f of p. Propagation of the spectrum of spatial spectrum in a uniform medium of an average. This is achieved by using multiplication with e power I beta k z. delta z, where beta k is given by is k 0 beta average is what I have used. Beta average square minus p square for every component, and inverse transform, inverse Fourier transform to get the propagated field. From f of capital F of this, let us say, results in f of p f propagated field of the kth element f propagated f inverse of f propagated field is a function of k or p, we have thought it as a p. Then finally, the application of the correction factor. By multiplying e power I gamma delta z. So, gamma is specific to that specific interval. So, in the simplest case, we have obtained gamma k to be k 0 delta n k, and of course, delta z is already included here. So, in each of these steps, we can store the necessary field components or extract some important information like propagation constants and so on and so forth. So, extensions, there are several extensions that are possible. So, extensions and variations. So, first of all, we need to consider what are the various factors involved in using this BPM. The most important one being the grid size. So, most often these algorithms are used in a digital way. That is, the Fourier transform is taken as a discrete Fourier transform rather than continuous Fourier transform, which requires dividing the given input beam or the structure into several x components, so that you can take a DFT. For example, an n point DFT is typically used. Similarly, we have the propagation grid along the propagation direction. So, we are discretizing along the propagation direction, that delta z also matters. So, these define the accuracy and utility of the method. The extensions of the BPM that have come in practice are various. Some of them are as follows. We have a vector BPM, where instead of considering the field as a scalar field, we can consider all the components of the field and get a system of differential equations and convert them into the beam propagation method. Similarly, we have ignored the second derivative component. The variation of the field is considered, we have reduced it to what can be called as a paraxial form. So, we have considered only the first derivative as representing something. So, this can be called as, we can incorporate more higher order terms and we can call it as a non-paraxial BPM. Where we can retain some higher order components, do more mathematics and get an improved value of the propagation or the factors. Similarly, when we are ignoring the second derivative, we are ignoring another important aspect called the back propagation, backward waves. We have considered the light wave propagating only along one particular direction. So, in many devices there could be reflections which could be accounted by using what can be called as a bidirectional BPM. Another important variation of the BPM which I will very briefly describe is called the finite difference BPM. We have considered the Fourier transform as a way for propagating the light across the uniform medium. We can extend it by using what is called the finite difference BPM, in which the derivatives are replaced by their differences. We use finite differences to replace the derivatives. I will just illustrate with a small example. Suppose we have a differential equation as follows. I have taken the earlier example where we have the first derivative with respect to z and the propagation is not replaced the Fourier transform, but retained as it is, where A could be a coefficient containing the structural parameters like the refractive index profile and all those things. So, we can replace this propagation factor by dividing into several small segments once again as earlier by using phi of, let me say, mth section, ith section delta I or k, let me put k by delta z. So, I have replaced in a iteration, mth iteration of kth element as follows, and then I will also replace the derivative with respect to x square. Of course, we can replace this with the corresponding value of a obtained at that corresponding segment. Let me write it in a 2D grid rather than a single 1D grid. So, we can replace the second derivative a, the right side component as a of x comma z d square phi by dz square dx square, as I will retain a of, let me say I will take it as m plus 1 point because we are m is in this direction and k is in this direction, discretization. So, let me call it in the middle of this segment like m plus half for the ith component, and then the second derivative will be replaced by of x will be replaced by m k plus 1, let me call it k minus 2 phi k m plus phi of m into k plus 1 divided by delta x whole square. So, there are many other ways to do the discretization with respect of the second derivative with respect to x. So, we have a left side as one factor and right side as one factor, and we can put everything in the form of a matrix and get a matrix equation to solve for the field profile psi. So, nowadays there are several commercial beam propagation methods, and more are needed depending on the new problems that we encounter in integrated optics, and I hope this description will give an insight into how things work, and I hope the readers can go to the standard literature and get a more accurate description of these. One of the typical references that I would cite just is the Pollock's book on optoelectronics. Where this reference I would mention at the end of the course, and there is a MATLAB program to do this Fourier transform BPM in that book. So, it could be directly typed in and executed just by changing the refractive index profile. You can apply to any problem like a taper or a Y branch or interferometer and so on. Thank you very much.